Now we analyze the situation where f doesn't approach anything but rather becomes unbounded as x approaches a certain number. So here, the first example we have is of the function f of x equals 2 over x minus 5. We notice here that as x approaches 5, the denominator becomes smaller and smaller, and thus the whole expression blows up as x approaches 5. So the limit of f of x as x approaches 5 does not exist. However, we may ask, what happens if we approach 5 from the right and from the left? And in this case, when we approach 5 from the right, as we can see from the graph, f becomes unbounded and very positive, so the limit is plus infinity. If instead we approach 5 from the left, then f of x becomes very negative and without bound from below. So the limit from the left is, we say it is equal to minus infinity. This is just notation to mean that f is either very unbounded or very positive or very negative. And what determines the signs here, so either plus or minus infinity, have to do with the sign of the denominator. So here the sign of the denominator depends on whether x is greater or smaller than 5. So when you encounter an expression like this, you see that, well, the numerator here is positive, so the sign of the whole expression will depend on the sign of the denominator. If x is bigger than 5, then x minus 5 will be positive, and if x is smaller than 5, you're subtracting something bigger than x, so that's negative. And that's where we get these signs here. So plus infinity if x is approaching 5 from the right, and minus infinity if we're approaching 5 from the left, because then on that side f is negative. And of course, if the sign of the denominator doesn't change, I mean it's the same whether you're on the right or the left, then the function may blow up with the same sign, like in this case, x to the fourth is a very nice function, except at the origin where it blows up, I mean, well, it becomes 0, so 1 over x to the fourth blows up at the origin. So again, we ask what is the limit as x approaches 0 from the right of f of x. And we can see from the graph here that is plus infinity, but we can also see that since x is approaching 0, 1 over something very small is blowing up. And the difference here with respect to the previous example is that the limit on the left is also plus infinity, and that is due to the fact that x to the fourth doesn't change sign. It's always positive when x is different from 0. It's always positive. And so the sign of that expression that is blowing up is always positive. Now we have an example of a function that is not even defined for negative numbers. So here f is not defined for x less than 0, less than or equal to 0. Actually, so we can only ask what is the limit of f of x as x approaches 0 from the right, because from the left f is not defined. And here we see that as we approach 0, natural log of x is just becoming more and more negative. So the limit here is minus infinity. And so as you see, I mean, there are many different situations and many different combinations. As you analyze functions, you may encounter points where, in fact, the function is blowing up on one side and it's bounded, it's approaching a limit on the right, or maybe oscillating like the sine of 1 over x and blowing up on the other side. So a lot of things can happen, but these are model problems that more or less tell you what are the possibilities. What the possibilities are. So let's look at some examples. Using what we know, these examples are taken from the book. There are some other more exotic problems there where you're asked to kind of try to see a trend numerically, but we'll leave those kinds of expressions to be analyzed later when we have the tools to actually deal with them instead of just approximating things numerically, for which you need a calculator. Here we'll do the analysis just using algebra. I mean, these are the kind of, I mean, in the exam you will not be asked to do heavy numerical computations, so those kinds of problems will not appear anyway. So, but we may ask you to do things and to perform operations, algebraic operations, which are easy to handle. So let's look at the example. The first example is something we already analyzed. If we try to compute the limit when x approaches 1 of square root of x minus 1 over x minus 1, first thing to notice is that the numerator and the denominator becomes 0 if we try to evaluate at 1. So we cannot just proceed by plugging in the value 1 in this expression. What we do instead is something we did a few videos ago. So we can rationalize here. So multiply by square root of x plus 1 and divide by the same thing. So this becomes square root of x squared in the top minus 1 divided by x minus 1 times 1 over the square root of x plus 1. Here, remember that we use the fact that if you multiply x minus y times x plus y, this is equal to x squared minus y squared. Okay, so this is a basic identity. So if we continue trying to compute the limit, this is the limit as x approaches 1 of, well, here notice, remember that whenever we're trying to compute limits, x is never allowed to take on the value which this expression becomes undefined. So we can be very close, but not at the point. So x minus 1 is not equal to 0. So we can cancel this, and we just get the limit of 1 over the square root of x plus 1. And now this expression here is well defined when x is equal to 1. And you see that, well, the numerator is just 1. But as x approaches 1, well, 1 is just 1, and so square root of x approaches 1. So we get 1 over 1 plus 1, which is just 1 over 2. Right, so if you allow me, we'll go over yet another way, so another way of looking at it. Another way, this essentially boils down to the same thing, it's just a matter of noticing that here in the expression we have the square root of x minus 1 over x minus 1 over x minus 1. This can be written as this. So the square root of x minus 1 is just the square root of x minus 1. And the bottom can be written as the square root of x squared minus 1. we're near 1, we're close to 1, so the square root of x squared is just x. And we use the same identity as before, which tells us that this is the same as the square root of x minus 1 times the square root of x plus 1. And here again, x is not allowed to take on the value 1, so we can simplify this and that to get the same algebraic expression that we evaluated at the end. Okay, so we can continue like before to obtain 1 over 2 as our limit. Now, let's look at this expression here, the second example. We want to compute the limit when x approaches minus 4 of 2x squared minus 32 divided by x plus 4. So if you look at the bottom, if you try to plug in minus 4, you get 0. But also when you plug it into the numerator, because minus 4 squared is just 16. 16 times 32. No, 16 times 2 is 32. So the numerator becomes 0 as well, so it's not defined. So what we do is we write this as 2. We factor. We take a factor of 2. 2x squared minus 16 divided by x plus 4, and then write this limit again as the limit as x approaches minus 4, and we use the same identity as before, so we have x squared minus 4 squared, so x squared minus 4 squared, which then is equal to x minus 4 times x plus 4, and we're dividing by x plus 4, and we again notice that x plus 4 is not equal to 0 because we're not allowing x to be equal to minus 4, so we may cancel these two terms here out. And what do we get? Well, 2 is just a 2, x is approaching minus 4, and minus 4 is just minus 4, so the whole thing is approaching 2 times minus 4, which is minus 8, times 2, which is minus 16. So that's the limit. All of these limits that we've been computing here can be computed using the same algebraic trick, which boils down to finding the factors that will cancel out in the expression that will allow to get an expression that's well defined at the point we are approaching. I mean, at the point that we would like to evaluate, so the point we're approaching. Okay, so here again we have yet another limit. The limit of x squared plus x minus 6 divided by x squared minus x minus 2 as x approaches 2. And you'll notice here that again the numerator and the denominator both approach 0 as x approaches 2. So the expression at the top becomes 4 plus 2, which is 6, minus 6 is 0. And the denominator is 4 minus 2 minus 2, which is also 0. Okay, so what do we do here? Well, whenever we have polynomials that vanish at a certain point, it means that we have factor of x minus the root and in this expression. So we can factor out an x minus 2 in the top and in the bottom. So x squared plus x minus 6 is equal to what? X minus 2 times x plus 3, right? So the coefficient in front of x is 1, so that means that we have two numbers that add up to 1, and the product is minus 6. Minus 2 plus 3 is 1, and minus 2 times 3 is minus 6. The bottom again, we have a factor of minus 2. Okay, so again, the same thing. We know this is x squared minus x minus 2 is just x minus 2 times x plus 1. Why? Because, well, the coefficient now in front of x is minus 1. Minus 1 is the same as minus 2 plus 1. And the free term here is minus 2, which is minus 2 times 1. Again, we are not allowing x to become 2. So x minus 2 is not equal to 0. So we may cancel these two terms. And now x plus 3 and x plus 1 are both well defined at 2. So we just plug that in, and that becomes 5 over 3. Okay, so our limit is now 5 over 3. One last type of problem you may see from time to time regarding the computation of one-sided limit is this kind of graph, kind of graphs that you're asked to analyze. And yeah, and so suppose like in this example we're asked to determine the one-sided limits at the points 1, 2, and 4. And we have to also state whether the limits exist at each one of these points. Okay, so if we look at 1 at x equals c equals 1, the limit of this is the function g, so the limit of the function g of x as x approaches 1, but from the left, so if we're approaching 1 this way, is equal to 3. So we see that if we move closer, we get closer to 1 from the left. G is this red line over here, and the values of G are getting closer to 3. Okay, so this is the limit of g of x as x approaches 1 from the left. Now the limit from the right at the same point is equal to 1. So now if we move here instead, we see that g of x is approaching this value, which is 1. Now, when we look at the point 2, we would do the same thing. The limit from the left of g of x is 1 again, and the limit of g of x from the left sorry, here I made a mistake. If we're approaching 2 from the left, then this is equal to 2, which is this value here. And if we're approaching 2 from the right, then we are approaching this value 1 over here. Okay. So finally, the limit of g of x as x approaches 4 from the right happens to be the same as the limit of g of x as x approaches 4 from the left. You see here there are no jumps in the graph of g. So whether you're approaching 4 from the left or from the right, you get the same thing, which is 2. So here this value 2 is also just the limit. Remember, when the one-sided limits are equal to each other, then the limit exists. Okay. In these two examples, this is 2 points. However, the two one-sided limits are not the same, and so the limit does not exist. At either point. But here it does. Okay, we'll finish in the next video with the limit laws, which are the very important way, a very important tool, give us very important tools that allow us to compute limits starting from known limits.